Okay, so welcome to our second morning session. Good news, this is our last morning session, so you might sleep more tomorrow. But bad news, this means that conference ends today, so let's enjoy together all remaining talks. The first one is by Marina Imocrante. Imocrante? Yeah, it's too difficult for me. And she's going to present the talk, this talk, Ontology and Application in Pincock's account, a weak link.
Thank you. So, in this talk, I will investigate the relationship between the epistemology of pure and applied mathematics in Christopher Pincock's account. After reviewing the main feature of his account of the different epistemic roles of mathematics in applications and his epistemological project for pure mathematics, I will move to criticism to Pincock, and I will present my attempt to solve those criticisms. In his account of the applicability of mathematics, Pincock wants to account for the presence of mathematics in our scientific representations, to see to what extent the central place of mathematics in science contributes to the success of science. Pincock is interested in the epistemic contributions of mathematics to scientific representations. Basically, mathematics helps in the confirmation of the accuracy of a given representation through prediction and experimentations. Pincock's inquiry proceeds moving between the philosophical reflection on the applicability of mathematics and concrete case studies from the scientific practice. So this is what I take to be the naturalistic aim of Pincock's proposal. The structural account of the applicability of mathematics is descriptive, as Pincock's book constitutes a rich archive of case studies of the roles of mathematics in scientific models, and it is a pluralist account, as each case of application could be different, and it is not possible to use a unique model to explain the functioning of every mathematical representation. This is why the description of several types of case studies is essential. The driving force of Pincock's account is the existence of a structural relation between a given physical situation and a mathematical structure, where a structural relation is a relation between two systems obtaining only in virtue of the formal network of relations among the elements of the systems, and the existence of this structural relation allows us to use the mathematical structure to represent the physical system. Thanks to this structural correspondence, scientific representations could be said to have a mathematical content. This content is what gives us the possibility to confirm our representations in providing conditions under which the representation is accurate. Central to the structural account are the endorsement of a form of semantic realism for mathematical statements, in virtue of which we can say them to be true, and the possibility to refer to mathematical objects as well as to physical objects. So this is why Pincock assumes semantic internalism for mathematical concepts, so that mathematical concepts could be sufficient to pick out their reference, and on the other hand, Pincock assumes semantic externalism for physical concepts. Pincock identifies several different types of mathematical representations used in science. I will not describe them here, and the mathematics provide also the conceptual skeleton of scientific representations, what Pincocks call constitutive framework. The constitutive framework of a given scientific representation is the foundational framework, composed by the basic scientific statements making an essential use of mathematical terms. Those statements are the statements whose acknowledgement make possible the formulation and the understanding of the scientific representations at issue. For example, the scientific content of the law of universal gravitation is made possible by the constitutive framework provided by Newton's law of motion, in which mathematical terms constitutively appear. So, the different epistemic roles of mathematics in science form what Pincock calls derivative representations, each being grounded in a mathematical constitutive framework. For the structural account, constitutive frameworks ought to be a priori justified. Here, Pincock is using a notion of a priori as the one endorsed by Albert Casullo, where a priori justified means non-empirically justified, but at the same time defeasible by empirical evidence. A defeasible belief is a belief whose justification is fallible, so a belief that could be falsified by experience. In this respect, Pincock refers to constitutive framework as both a priori and relative. At the same time, Pincock explicitly states the practical need to have an absolutely a priori justification for the beliefs of pure mathematics constitutively employed in scientific representations. This is a practical demand, since an a priori justification is needed in order to decide if we have reason to believe our pure mathematics to be true, and consequently in order to be able to confirm our scientific representations. Pincock claims that his account of applicability is endorsable independently from any particular ontological position and compatible with anti-realist positions, claiming that the only necessary requirement in his account is to endorse a form of semantic realism. But we can say that Pincock's epistemological account for applied mathematics states a weak relation of dependence of the application of mathematics on its ontology, a relation of logical dependence, not a metaphysical dependence. Because despite declaring the independence of the application from the ontology of mathematics, a connection could nevertheless lie in his demand of a priori justification of the beliefs of pure mathematics constitutively used in scientific representations. This is because, as I will contend, the demand of a priori justification can be seen as entailing a form of ontological realism about mathematical objects, although Pincock denies this. And the weak link I see between ontology and applications in Pincock's structural account lies in this relation of logical dependence of the applications on the ontology of mathematics via a priori justification of beliefs of pure mathematics. So, concerning the epistemology of pure mathematics, Pincock's first concern is to end up with a plausible reconstruction of the history of mathematics. Pincock expresses the naturalistic requirement to account for the development of mathematical concepts and theory through the history of mathematics, what he calls the historical extensions of mathematics, drawing on Mark Wilson's non-classical account of physical concepts. I quote Pincock, "The extension-based strategy I have in mind starts with the assumption that mathematicians have achieved some degree of mathematical knowledge at some stage in the history of mathematics. It is not reasonable to assume that the concepts themselves are sufficient to provide the evidence in favor of a substantial mathematical claim." So Pincock is refusing here an exclusively concept-based approach, as Pincock 1, for example. On this approach, on the contrary, the evidence comes in form of the proofs provided. So on this approach, the knowledge available in a mathematical context provides a crucial part of the evidence in favor of a new mathematical claims. Pincock's example of the extension of mathematical concepts concerned the concept of square root function. And basically, despite its definition as a function on non-negative real numbers, the definition of the square root function can be given for complex numbers, and the proper setting, in this case, the proper setting for studying this function can be a Riemann surface. So in this way, the concept of square root function is extended in some sense. So I quote Pincock again. With the square root function, what an extension-based epistemology must confront are the steps that mathematicians like Riemann and Weil took to argue that, in fact, the best way to approach this function is a single-valued function on the Riemann surface. This argument is ampliative. It involves a conclusion that goes beyond previously known theorems and relevant concepts. Pincock's suggestion is that the sort of argument used here is a purely mathematical version of the inference to the best explanation. Like the inference to the best explanation in scientific case, an appeal to the right Riemann surface in this case helps explain the peculiar multi-valued appearance of the square root function. These explanatory considerations are evidence that the new collection of claims about the square root function are correct, Riemann was justified in presenting these claims, and arguably he knew them to be true. So basically what Pincock is presenting is an epistemological strategy for pure mathematics that confronts itself with the historical steps of the development of particular mathematical concepts in order to know whether we are justified to believe our mathematical claims to be true. But following Pincock, this strategy would be consistent with the conclusion that the beliefs of pure mathematics are a priori justified. And in this framework, to justify a priori the beliefs of pure mathematics for Pincock means to justify them, as we already saw, independently from empirical experience, internally to pure mathematics, and prior to their use in science. What Pincock has in mind here is an epistemic priority. If we do not have reason to believe the relevant statements of mathematics to be true, we will not have reason to believe our scientific representations to be true. Okay, now I come to my two criticisms. As for the first one, I will contend that in Pincock's epistemology of applied mathematics, the demand of a priori justification of the portions of pure mathematics, constitutively used in scientific representation, commits one to endorse ontological realism about mathematical objects. Consequently, this demand does not fit with the declared independence of Pincock's account from the endorsement of any particular ontological position. I contend that Pincock's account of the applicability of mathematics depends on ontological realism about mathematical objects due to its demand of a priori justifications of the portions of pure mathematics used in scientific representation. So what I will contend is this argument. The a priori justification of pure mathematics entails ontological realism about mathematical objects, and given that Pincock's structural account of the applicability of mathematics requires some a priori justification of the beliefs of pure mathematics, so Pincock's account depends on ontological realism. We saw that in his account, Pincock only argues for semantic realism for mathematical statements. Notice that Pincock's argument for semantic realism is a posteriori, because it is in order to endorse the epistemological account of applied mathematics he proposes that a realism about the truth values of mathematical statement is needed. Now, in adopting realism about the truth values of mathematical statements, it is not obvious to keep this position separate from a form of ontological realism for mathematics. In particular, within Pincock's proposal, I submit that it is legitimate to go from realism about truth values of mathematical statements to realism about mathematical objects. For example, consider the semantic requirements stated for mathematical statements by Benassarov's paper, Mathematical Truth, that a statement ought to be true in virtue of the things that it is about, and that two statements of the same logical and grammatical form ought to have analogous truth conditions. In this case, a mathematical statement and a non-mathematical one that share the same logical grammatical form ought to have the same truth condition. If a referential semantic is endorsed, the truth condition of the non-mathematical statement will refer to objects. That statement will be true because certain objects stand in a certain relation to each other. And notice that Pincock would agree with the standard referential semantic interpretation of non-mathematical statements, since he assumes a semantic externalism for physical concepts. So, if the truth conditions of non-mathematical statements refer to objects, then, as for mathematical statements, in a standard referential semantic, their truth conditions must refer to objects too. So, a given mathematical statement will be true because certain mathematical objects stand in a certain relation to each other. Now, in considering the general perspective of Pincock's structural account, we can notice that within this framework, this passage from realism about truth values of mathematical statement to realism about mathematical objects via standard semantics is legitimate. First of all, the structural account explicitly requires the possibility to refer to mathematical objects as well to physical objects, so that the structural relation between a given mathematical structure and a given physical situation could be established. It should also be noticed that within the constitutive frameworks of scientific representations in Pincock's account, physical and mathematical statements are mixed up and put at the same level. Moreover, the initial distinction stated by Pincock between semantic internalism for mathematical terms and externalism for physical terms seems to be retracted when it comes to constitutive frameworks. Because, as an example, considered in the following quotes, a plausible requirement, Pincock says, is that these mathematical terms must correspond to the genuine features of the things I went up referring to using the new word. And again, when it comes to logical and mathematical terms, it is considerably more plausible to consider the meaning of a new term as being fixed by the adoptions of rules. But contrary to Carnap's semantic internalism, these rules might involve rules that reflect the features of the object in question. So, considering all this, I submit that in a perspective as Pincock's one, the passage from semantic realism to ontological realism via standard semantics cannot be avoided. This is why I argue for the necessity of a form of ontological realism about mathematical objects in Pincock's account of the applicability if he wants to maintain the a priori character of the justification of mathematical beliefs. Just to clarify my argument, if constitutive frameworks are taken to be as a priori justified in order to have reason to believe their pure mathematical parts to be true, then we adopt a semantic realism. And this semantic realism entails an ontological realism by standard semantics. Consequently, our mathematical representations and our fully scientific representations, being grounded in constitutive frameworks, would turn out to be grounded in an ultimate ontological realism. So, to solve this first criticism, the easiest solution I see is that in order to maintain the demand of a priori justification of mathematical beliefs in the core of its account of applicability, Pincock accepts the dependence of the application of mathematics on its ontology in its structural account, grounding its epistemology for applied mathematics in a realist position regarding the ontology of pure mathematics. But here we come to the second criticism concerning Pincock's epistemological project for pure mathematics, because I submit that this project for pure mathematics is animated by two diverging requirements, the one of justifying mathematical beliefs a priori on the one hand, and the one of taking into account the historical development, as we saw, of mathematical concepts on the other. Now I will briefly highlight some problem in the compatibility between these two requirements, and thereafter, given the general aim of Pincock's proposal and the ontological problem posed by the demand of a priori justification we saw, I will submit that this demand should be abandoned by Pincock, the demand of a priori justification for mathematical beliefs, in favor of the naturalistic demand of accounting for the historical developments of mathematical concepts. So, first of all, consider the method of inquiry that Pincock proposed for the epistemology of pure mathematics. He presents the reader with a detailed example of the analysis of the historical development of a particular mathematical concept, the already quoted example of the square root function, and draws theoretical claims from it. This is why I contend that the method of inquiry for the epistemology of pure mathematics proposed by Pincock is as descriptive as the method he adopted for the analysis of the applications of mathematics. So, in Pincock's account, the reasons a scientist has to believe the statements of pure mathematics of a particular constitutive framework to be true seem to come from the specific historical cases of the development of this and that mathematical concepts. So, historical considerations here count in favor of the justification of mathematical concepts. And it becomes really difficult to see how this situation could be comparable with the stated requirement of a priori justification of mathematical beliefs. Moreover, there are at least two distinctions that should be made in order to clarify Pincock's epistemological proposal for pure mathematics. First of all, the general necessity of taking into account the historical development of concepts and theories through the history of mathematics on the one hand, and the understanding of particular cases of the development of certain concepts and theories of pure mathematics on the other are not clearly separated. To see this, consider that the description of Pincock's extension-based epistemology for pure mathematics is difficult to articulate leaving behind the specific features of the particular example proposed. Secondly, Pincock says to distinguish between the experience necessary to acquire a concept and the experiences that figures in the justification of a belief involving that concept. This distinction in itself is clear, but it is not clear how this could be made within Pincock's descriptive account, because in his example of epistemology of pure mathematics, he wants to take into account both a priori and historical considerations, but in the end, the only considerations internal to mathematics he offers to justify mathematical beliefs consist in recalling the historical development of the concepts and theories at issue. So this is why I submit that this approach to the justification of the statements of pure mathematics is difficult to be conciliated with the requirement of a priori justification of mathematical beliefs. And to solve this criticism, I submit that given the general descriptive and naturalistic aim of Pincock's epistemological proposal, it would be more consistent with his approach to abandon the requirement of a priori justification in favor of the contrasting one of taking into account the development of concepts through the history of mathematics. As we saw, this is because a justification of our mathematical beliefs showing how mathematical concepts and theories originate in response to the previous mathematical knowledge and the developments of mathematics is certainly a justification internal to mathematics, but it could not be an a priori justification resting on the history of mathematics. Moreover, the methodological choices characterizing Pincock's epistemological inquiry concerning both applied and pure mathematics are more suitable for the study of the historical development of mathematical concepts than for the theoretical inquiry about the a priori status of justification of mathematical beliefs. So, to sum up, I moved to criticism to Pincock in order to solve the first concerning the dependence on ontological realism of his account for applied mathematics. I submitted that Pincock has to adjust the relation between the application of mathematics and its ontology by accepting the dependence of the former on the endorsement of a realist ontological position about mathematical objects in his account, and to solve the second criticism concerning the two diverging requirements. I submit that it would be consistent with the descriptive aim of Pincock's proposal to abandon the requirement of a priori justification of mathematical beliefs in favor of the naturalistic demand of accounting for the historical development of mathematical concepts. So, to conclude, let me maybe just clarify the relation between those two criticisms, because the basic problem is that Pincock wants to take both a priori considerations and historical considerations into account in his epistemology. And what I am doing here is to show that these two requirements are in contrast to each other, second criticism, and that in maintaining the requirement of a priori justification of mathematical beliefs, Pincock will commit his account to ontological realism, first criticism. So, in my opinion, one would have to follow the solution I proposed to the second criticism, abandoning the requirement of a priori justification. Of course, my first criticism in this case would collapse, but it will be okay because this is my positive proposal, and because this is the solution I think it's more consistent with the descriptive and naturalistic aim of Pincock's account. On the other hand, one could also choose to follow the solution I proposed for the first criticism, so accepting ontological realism about mathematical objects, and arguing that my second criticism would, in this case, turn out to be inconsistent. In this last case, I will answer by highlighting that this choice, I mean the choice of adopting of endorsing ontological realism and favor the need of a priori justification of mathematical beliefs over the need of accounting for the history of mathematics in the appropriate way, this choice will contrast with the naturalistic aim of Pincock's proposal. So this was just to clarify. Thank you for listening.
Okay, so questions? Okay. Yeah,
maybe.
okay, we're good. It's better with the microphone.
Okay, thanks. That was really nice. Actually, I have a clarification question and a very general comment. The clarification question is you had the slide with an arrow from a priori justification to semantic realism and another arrow from semantic realism to ontological realism. I understand that you criticized the second arrow, but I just didn't get why Pincock needs semantic realism to have a priori justification. And the general comment I have concerns the strategy that some people might deploy to have both a priori and some sort of naturalistic take on justification. And the idea is to distinguish between enabling role of experiences, for instance, and justificatory role. So maybe, but this is, I mean, very rough suggestion. Well, one way one could go in your account is to try to preserve a priori by saying, well, all this history of mathematical practice plays an enabling role. But what really justifies are our, armchair considerations based on the history of mathematical practice. And this maybe in this way, Pincock could save both aspects of the. I don't know what you think.
Okay, so about the arrow from a priori justification to semantic realism, I mean, maybe the arrow was not a good choice, but the symbol. I mean,
no, but it's not about the symbol.
The problem is that I'm talking really about Pincock's account. So, I mean, in his position, and his position focuses on the epistemology of applied mathematics. And in this position, semantic realism is needed because you have the need to consider mathematical statements to be true in order to establish a relation, a structural relation between mathematical structure and the physical system you are representing with the mathematical structure. This is why you need semantic realism. And he states the practical need to a priori justify these the mathematical beliefs involved in your mathematical claims, because he refuses a posteriori argument for semantic realism. For example, a kind of a form of indispensability argument. For example, a form of indispensability argument. He refused this because he thinks that the a posteriori justifications for mathematical beliefs are not enough. But what I'm contending is that, in fact, his account has the resources to give only a posteriori justifications, not a priori.
Okay, so Neil?
My question was essentially the same.
Okay. Marco?
Yes, more or less the same thing, but my point is more radical. I see no principal reason to think with this expansion. So basically the same, but it's more radical point. I see no principal reasons to see a tension between historical development and also the fact that you consider historical development as a sort of justification with the idea that the mathematical justification is a priori. Euclid justified his theorem in geometrical theorem axiom in geometry in a certain historical situation. So if you want to reconstruct the justification, you have to go there, but the justification are perfectly a priori. I don't see where the problem is.
Yes, I can agree with you, but I was talking about attention in Pincock's account. So what I am saying is that these distinctions that I highlighted and clear are distinctions that are clear distinction in themselves. But in Pincock's account, Pincock in his description of the epistemology of pure mathematics doesn't clearly separate these issues. I think he wants to argue for
Sorry, I don't see the problem of separation. Take another example. The more clear example of an a priorist approach to mathematics, Frege. If you wanted to study Frege, you want to understand the way in which Frege considered mathematics could be justified by logical consideration, you have to take Frege's book. Frege's books are written in a certain historical period. The logic that Frege uses is not exactly our logic. There is a lot of differences, so you have to consider the difference. The logic, Frege's logic came from a reflection to prior logic. Development of Frege logic brought to our conception of logic. All that is historical development. But of course, Frege argument is perfectly a priori.
Of course, but he doesn't mix up, Frege doesn't mix up in his argument the particular cases of the justification of particular belief, grounding it on the history of the mathematical concepts at issue, and use it to say, I'm justifying a priori my belief, my mathematical beliefs. What I'm saying is that in Pincock's account, it seems to be this problem of confusion of plans between particular cases and the general
You wanted to say that
account.
what to justify, according to Pincock, justify mathematical belief is the mere historical development, and not what in the historical development is considered to be a justification.
Yes, I want to say this in the sense that I think that Pincock's account has the resources to do only this for the descriptive way he presented things.
Davide?
A very brief question about one issue that was not central, but I was interested in it and I was hoping you could say something about it. There are some earlier papers where Pincock, although he probably is already endorsing something like a structural account, still discusses examples where he talks, for instance, about abstract explanation, where he seems to make room for a sort of more varied portrait of how mathematics enters applications. I wonder whether in the monograph overall you think is just blocking the way to this variety and sticking to a very specific model of.
Okay, yes. In fact, in this book, in the 2012 book, Pincock ampliates his account, his mapping account. The mapping account he presents, he already presented in earlier articles, and I didn't describe it here, but he gives a lot of examples from mathematical practice about applied mathematics. So the account is very rich in this sense, and it has the resources to describe very different cases of applications, very different from each other. My problem was in the 2012 book, he focuses on the importance of justifying in some way the pure mathematics that you use in scientific representation. So in the second part of the book, the focus moves to the justification of pure mathematics, and in this case, it seems to me the problems I see are in this second part.
Samantha?
So here's the crazy idea of
Yes, can you?
Okay.
Could you say we should be interpreted in a kind of Kantian way? So The a priori justification is a priori just in the sense that it's a fact about observation. And the structural relations between the physical systems and the mathematical structures also justifies it straight out of the way that we impose structure on the world. So the way that Kant thinks about time is could be similar to the way that thinks about the immutability of maths.
Okay, maybe it's possible, and maybe I think that in some paragraph of the book it can also give some indication in this sense, in the sense that he's talking. Sometimes he talks about in a more cognitive sense, but he talks about the way we understand mathematical concepts and so on. So, but I have to think about it.
So, like, I mean, take that seriously, that it gets rid of the priori justification problem and the ontology problem, because the structural relations are essentially higher.
Okay, maybe I don't know. Maybe in this case, the a priori justification, the problem about the a priori justification will be solved. But I'm not sure about the relations with the ontology in this case, if we take this route. But I will think about it. Thank you.
Okay, so 2 minutes break. Then we will be back.